As part of the Erdös Data Science Bootcamp for the spring, we predicted Alzheimer's disease using health-related features. 1 in 3 older Americans die from Alzheimer's. Healthcare costs alone is projected to reach $1 trillion by 2050. This growing impact motivated our goal for this project, which is to use machine learning to predict Alzheimer's early enough by developing predictive and probability models that have high-performing metrics. Key stakeholders in our project include healthcare professionals, researchers, and patients. We used a synthetic dataset from Kaggle that had 2,149 patient records aged between 60 and 90. The dataset contained 34 features grouped under these 6 broad categories. Our target variable was the Alzheimer's diagnosis. Also, we were fortunate to have a clean dataset. As you can see, there are no outliers in this box plot. We also had a case of no multicollinearity. It's interesting to note that only the cognitive features had a strong correlation with the target variable. To highlight the value of cognitive features, we ran a PCA model for just cognitive features and all features, and we realized that there was a better clustering for the cognitive case, showing a stronger link to the target variable.
For our modeling strategy, we splitted the Kaggle training set for validation purposes. Various classification models were tested and compared against the baseline, which was the most frequent target class. Models were run on different feature subsets to assess their impact. For early detection, we repeated this process on patients without memory complaints. Using accuracy as the metric, we selected and tuned the best performing models, which were ADA-Boost for full dataset and XGBoost for patients with no memory complaints. ADA-Boost showed the best performance with accuracy score of 96.5% when we consider the entire dataset. For the dataset restricted to patients with no memory complaints, the best accuracy score was 95.6%, and this was from the XGBoost model. In view of this, we selected both models to tune and to explore the possibility of an even improved performance for both cases, respectively. For hyperparameter tuning, we used Optuna for the best performing models, which were ADA-Boost and XGBoost, optimizing various metrics to penalize different sources of inaccuracy. Scores were obtained using both five-fold cross-validation and full training set fitting. For the validation set with known target value, confusion matrices were compared, while for the Kaggle test, the competition measured F1 score. The tuned models slightly outperformed the initial ones. The best F1 score from the Kaggle competition was roughly 93%, which is close to the leading score of 94%. For the entire dataset, ADA-Boost tuned with full training set fitting still outperformed the other candidate, while for the early detection purposes, XGBoost tuned with five-fold cross-validation still showed a better performance.
We analyzed feature importance for both the full dataset and the one with no memory complaints. In both cases, cognitive features and scores like MMSE, functional assessment, and ADL were the most influential predictors. These are coded in pink in our plots. In a medical context, it often makes more sense to talk about a patient's risk probability rather than giving a binary yes or no classification. So we calibrated our models to predict the risk of getting Alzheimer's and grouped the patients into low, medium, and high risk. The confusion matrices on the right show that our model mostly assigns low risk to non-Alzheimer's patients and high risk to Alzheimer's patients. Next, we explored how important features relate to Alzheimer's risk. We see that memory complaints and behavioral symptoms are associated with higher risk, while better scores on cognitive assessments are linked to lower risk. In this table, we see that for different levels of cognitive scores, our predicted risk aligns well with the empirical one. To summarize our work, we modeled Alzheimer's diagnosis for all patients and for those without memory complaints. Our best performing models achieved high validation accuracies and F1 scores of around 96 to 97%. We noted that cognitive impairments were the biggest red flags. Exhibiting these symptoms doubled the Alzheimer's risk. Moving forward, we aim to apply this model to real-world data and build a user-friendly risk assessment tool. Finally, we'd like to thank our mentor, Jamile, Stephen, and the entire Erdös team for their support.